All right, I'm ready. Welcome back. Sorry to keep you waiting. Let's continue. We got homework due tomorrow. There's actually one little thing on the homework that I was hoping to get to before I gave you the assignment. So we're going to get to it right now, though. I don't know if you may have figured this out on your own, but I wanted to try a couple of these repeating decimal problems where more than one digit is repeating. So this is something that we were talking about last time. Maybe I'll just refresh your memory about the most important thing that we talked about last time was the geometric series. And that's a series which looks like this. A times r to the n minus 1. And this converges, so there was a theorem from last time that you definitely need to know. This, if absolute value r less than 1, it converges to a over 1 minus r. That was the magic formula. And if absolute value r greater or equal to 1, it diverges. So this is how you handle a geometric series. And many of the questions in the second part of the homework are about this. And the old repeating decimal questions are also about this. Now we did an example last time with just like a single digit of repetition, but let's talk about a fancier one. So this is all on the general theme of converting decimal to fractions, right? If the decimal doesn't repeat, then it's always easy to turn it into a fraction, like, 0.729 is the same as 729 over 10,000 or something like that. Like if the decimal just goes a certain number of places and then it ends, that's always easy to convert to a fraction. But a repeating decimal is more interesting, more difficult. How about, let's try 0.737373, all right? Here we have two digits repeating. There are a couple on the homework like this, and I just want to do one in class. It's not all that different from the ones we did last time. The idea is you write this out as an infinite sum. So this I'm going to write as, the difference from last time is rather than digit by digit, I'm going to take it in sort of blocks of 2 digits each. This is 73 hundredths, right? Plus this would be 73, I guess, 10,000ths. I'm thinking of it like this: 73 over 100. That's the first underlined 2 digits, 73 hundredths. And then the next underlined 2 digits would be 73 over 10,000. All right, I'm taking two more zeros in the denominator every time. And this is 73 millionths, etc. And hopefully we can express the thing on the right-hand side as a series and then actually add up the series and get some answer. So on the right-hand side, I see 73 over 100. I'm going to write this as powers of 100 now. This is 73 times, I mean powers of 1 over 100, right? 1 over 100 to the 1. The next one is 73 times 1 over 100 to the 2. 73 times 1 over 100 to the 3, etc., right? This is indeed a geometric series because it involves, just a constant multiple times increasing powers of a single number. All right, so we should be able to add up the series. Remember, this involves finding what is the A and what is the R. So the A here, actually maybe this may even be easier not looking at these ones. It's probably easier to just take what I started with here. Anyone remember, how do you find the A? What's the A in this case? Yeah? 73, the A is always equal to the first term. 73 over 100, yeah. A is always the first term, 73 over 100 in this example. And then the R is the ratio, each term divided by the previous term. So I'm going to take the second term, like this one here, divided by this one. So this is 73 over 10,000 divided by 73 over 100. And then simplify this is like that. And I'll write the other one as a reciprocal. So the 73s cancel. A lot of the hundreds cancel. I think the answer is just 1 over 100. Right? That's the R. So first of all, you should ask yourself, does it converge or not? And the answer to these questions is given by the thing that I wrote at the top there. If R is less than 1 in absolute value, then it converges. And here my R is 1 over 100, so it is less than 1 in absolute value, and so it converges. So it converges, keep down there, to A over 1 minus R, which is, and this is what we're really interested in, 73 over 100 divided by 1 minus 1 over 100. That's 73 over 100 over 99 over 100. And if I just canceled them hundreds, 73 over 99 is the answer. And this one, very easy to check on your calculator. Just do 73 divided by 99, and you better get 0.73 repeating. Right? Any thoughts about that one? So you'll see a couple like this on the homework, which I hope will go okay for you. All right, great. Now you know you can do this really for any repeating decimal. Convert it back into a fraction. It is possible. All right, excellent. Great. Let's move on to a little, well, not quite ready to move on exactly yet, but really I suppose we're moving on. This is all that I wanted to say about geometric series. And this theorem right here is super important, and we are going to come back to that even after, we're not done with that stuff just yet. But for now, let's not talk about geometric series anymore. One thing to say is general rules for series. These are some more sort of simple but super useful rules. It says this is very similar to rules that we had for limits, although some of them are a little different. It says if the series AN and the series BN converge, then we can do some tricks. I'll write this like a theorem. The first thing, the sum CAN. Anyone want to suggest? What can we do with that, where C is a constant? There's some rule about this. If you're adding up a bunch of stuff, but you're multiplying by this constant every time. What can you do with that? Can you do anything with that? Pull it out. Yeah. You can move the C outside of the constant. C, sum, AN, right? Yes. There's a name for this rule, and actually this is, I'm sure, anybody know the name of this? Something you all do know this name, which I'm about to say. This is called the property. Anybody recognize this? This is something you've heard of, I'm sure. If I were to write this out, you don't have to write this down, but really what I'm talking about is something like the C is just some number. Like what if it's 2AN? What that means is it's 2A1 plus 2A2 plus 2A3, right? You're adding everything up, but you're just multiplying by 2 every time. And what I'm saying in the property is that actually you can bring the 2 out front and say, really, this is the same as 2 times A1 plus A2, etc., right? What is that called? This is the property.
It's like the constant multiplier.
Yeah, although like the 7th graders don't say that. The distributive property, that's what I'm looking for here. Yeah, this just says if you have a constant on the outside of a bunch of stuff added together, that's the same as if you distribute the constant across the stuff added together. Yeah, everybody knows the distributive property. Big D. The distributive property, right? That's what that is. Okay, what about, I got another one here. You don't really need this clogging up my list of, whoa, sorry. Get out of here. I don't want this clogging up my list. That is the distributive property. Another one, how about this? This is the same as the sum an plus the sum bn. So if you have terms added together inside of a sum, you can break up the sum into 2 separate parts. Actually, this also has a name that everybody knows. Anybody recognize this property in the same vein as the distributive? There were some other. This is the, remember your old properties from, I don't know when people learn this, yeah? The addition property? Yeah, I guess. I mean, you could say that. I would like to use one of those words ending with iv. There are like other properties, right? Am I the only one who's heard this word before? You'll know what I'm talking about, right? All right. Everybody's like avoiding eye contact. This one is one of those things also. Anybody recognize this? If I were to write these out, just the first few terms, I'll do this in red again. This one here, what that means is like A1 plus B1, and then A2 plus B2, and then A3 plus B3, right? Whereas this one here, it has like all the A's first, and then all the B's. Yeah? Yeah, this is the commutative property, which says when you have stuff added together, you can rearrange the order. All right? That's called the commutative property. Thank you for your 7th grader knowledge. Is that when people learn about this? I think I learned about these. I don't know when people learn these words. The commutative property. Yes, that is the commutative property. It's about rearranging the order, moving stuff around. That's like commuting. Is all about moving around. And surely you also remember the associative property, although there isn't a very convenient way to write an associative property for series. So we're not going to write an associative property for series. All right. And can I just also write, that same rule works with minuses. So this is sort of unsurprising, but this is another, I suppose, version of a commutative property, where you are moving stuff around but keeping minus signs in front of various things. Now, you may be tempted to ask, so this is the end of the theorem. Those are the important rules about series that we are going to use. One thing that you might wonder about, what about multiplication? Can you do this? Right? That's, I mean, like this one here, like this commutative one, but it's using multiplication instead of addition. This actually is not true. This one is actually false. Why is that? Think about what we're saying on either side. So the thing on the left would be, if I were to write out the terms, A1, B1 plus A2, B2, etc., right? Whereas, so that's this one. This one here would say A1 plus A2 blah, 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 times B1 plus B2 plus etc. All right? And are those actually the same as each other on either side? Can you really, if I have something like this and something like this, can I just multiply them one by one? The first two things, that's here, and then the next two things, that's here. The answer is no, that's not allowed at all. Like if you were really trying to work with this, you would have to do some kind of like insane infinite FOIL, right? Because of the multiplication here. You definitely won't get this as the answer. It's just not true. This is not even true. Like this is, I'm saying something about infinite sums here, but this is not even true, even if it's just like two things added together, because this version of it you would have to do the FOIL, and this one you're not doing the FOIL. So these two things on either side of the equal sign, they are very different, and that's why we are not talking about multiplying two series together. This is a much more complicated operation than just multiplying the terms together. All right, but anyway, all of those rules, so there is no such rule about multiplication, but these rules here about constant multiples and addition, they really do work. So we can simplify, like, for example, if I ask you to evaluate this series, or say that it diverges. Evaluate the answer or tell me that it diverges. This is complicated looking on its surface, but we can do those rules that we set up there. So one rule is I'm going to break this apart into two series across the minus sign. So this I can say is the sum of 5 over 3 to the n minus the sum of 3 to the n over 2 to the 2n. All right. And I could also factor the 5 out of the first one, just for fun. This is 5, the sum 1 over 3 to the n minus the sum 3 to the n over 2 to the 2n. All right. And now each of those two things have just n's in the exponent, and so we should be able to evaluate those two things separately as geometric series. Like this one here, if I were to write out the terms here, they would be 1 over 3, 1 over 9, 1 over 27, etc., right? I'm writing this out so that I can find the a and the r for that part, and then evaluate it. And then we could do a similar thing for the second part. This one here, these terms look like, this is a little more complicated, but I'm just going to plug in n equals 1. I get 3 over 2 to the 2. That's 3/4. N equals 2, I get 3 to the 2 over 2 to the 2 times 2. Just the first two terms should be enough for us to find the a's and the r's, right? So for the first one, I get a is 1/3, and the r is, remember, just because a is the first term. R is the second term divided by the first term. That's 1/9 divided by 1/3. And if I simplify that, it's 1/9 times 3 over 1, which is 1/3. All right. So that one, the r is 1/3, so it does converge. 1/3 being less than 1 means that that one converges. And then this other one here. So this, if I were to write these, this is 3 over 4. This would be 9 over, make sure you multiply these in the right order. That's 2 to the 4, right? And 2 to the 4 is 16. So this one, a is 3/4, and the r is 9 over 16 divided by 3/4. Which is 9 over 16 times 4/3. Cancel, cancel. That's 3 over 4. Right? And that is also less than 1, which means they both converge, and we should be able to add them both up. So they both converge, and they equal. So I had 5 times, remember the 5 which I factored out, and then I'm going to do a over 1 minus r. That's 1/3 over 1 minus 1/3. Minus, that was the first one, a over 1 minus r. And then the second one, a over 1 minus r. 3/4 over 1 minus 3/4. And this is the answer, whatever that is. If you want to simplify, this would be 5 times 1/3 over 2/3, which is a half, minus 3/4 over 1/4. So that's 5 times a half minus 3. Negative a half, I guess, if you want to go all the way with that. All right, so anyway, it means even if I give you a fairly complicated one to start with, You can split it up and work out the pieces and get a specific answer for what the sum equals. Or perhaps you might say it diverges after doing a bunch of stuff. All right? I got one like that for you to try. See how you like it. I would like you to try evaluate the sum 3 over 2 to the n plus 4 to the minus n over 3 to the n over 2. How you like that? See what you think. Do the same old stuff, split it up, and then evaluate each part. Feel free to chat with your friends about it. Because of the way you did it, I'm going to do slightly different steps. Get something that looks like All right, can we talk about these? People seem to be doing fine. Most of you don't want to talk to me, which is fine. This one, doesn't really require a whole lot of talking, I suppose. There's a lot of just working out the details. So the first of the two sums is fairly straightforward. Here, if you were to write the terms out, it looks like 1/2, 1/4, 1/8, etc. So the a is 1/2, and the r is 1/4 divided by 1/2, which is 1/4 times 2, which is 1/2. So I hope you got those a's and r's for the first one. And the second one is similar, but very, much more complicated looking, but you're doing the same thing though. So if I were to write the first term, it looks like that, using n equals 1. And then using n equals 2, it looks like 4 to the minus 2 over 3 to the 2 over 2. So this is, that's what that is. 3 to the 2 over 2, of course, is just 3, right? And 3 to the 1/2 is root 3. So if I were to do my a's and r's, the a is 4 to the negative 1 over root 3, which is the same as 1/4 root 3. I find that easier to make sense of. And then the r is the ratio of the second one. This is a little taxing to do. Divided by the first one, 4 to the minus 1 over 3 to the 1/2, right? I'll write root 3 for that. So this means 4 to the minus 2 over 3 times the reciprocal, root 3 over 4 to the minus 1. And then we cancel. These minus negative exponents, maybe just because they confuse me, I will write them sort of the right way around by putting what used to be a negative exponent on the other side of the fraction bar, like that, right? And then when I cancel here, 4 squared on the bottom cancels a 4 on the top. This is just root 3 over 3 times 4. Right? Root 3 over 12. Anybody agree or disagree? As I was walking around, if you simplify this differently, you'll write it in a different form, which is probably still correct. But for instance, if I multiply the top and the bottom by root 3 now, it'll say 3 over 12 root 3. That's also the same. And there are other ways you could write this also. All right. If you multiply the top and the bottom by 4, you can make it say something like 4 root 3 over 48 or something. Anyway, that's the r that I'm going to use for the second part. Now, you should actually think briefly about this r. Is that less than 1? Anybody have an opinion? The answer is yes, it is, although I'm not sure how obvious that is exactly just by looking at the fraction. You can always plug that into your calculator if you're concerned. Although, I suppose it is kind of obvious. I mean, this is less than 1 because the denominator is bigger than the numerator, right? Like 12 is bigger than root 3, isn't it? Root 3 is something like 1 point something or other. So yes, it is. This fraction is less than 1. You should at least think about that briefly, though. Anyway, it all converges, and so my final answer will be 3. There was a 3 coefficient in front of the first sum, and then a over 1 minus r, like that. I think that stuff in the parentheses is just 1. And then plus the other sum, I again do a over 1 minus r. This is the a over 1 minus r, like that. And I will just say that's my answer. I'm sure there are various ways you could try to simplify the second thing. I don't think you can fully simplify it because of the root 3's, but I don't really care. All right. Any thoughts about that one? I hope you got something like that. Great. All right, so this is really the end of doing examples involving geometric series. Geometric series work out quite nicely because of the a over 1 minus r formula. Other types of series do not have such interesting formulas. Anyway, this geometric is like, 1 plus 1 over r plus 1 over r squared, 1 over r cubed, right? That's what a geometric series, I didn't mean to write all those 1 overs. I don't know why I did that. This is what a geometric series looks like. And sometimes it has the 1, sometimes it doesn't. But it's like that, right? There is an important variation, I suppose. It's not really variation, just like another kind of series, and it's called the harmonic series. Unfortunately, you just have to remember these words. Geometric means powers of one number over and over again, the same number to different powers. The harmonic series is another important example, and it is this. It is the sum of fractions having increasing denominators. That 1 on the front, you might prefer to think of it as 1 over 1, right? Of course, that equals 1. But this is called the harmonic series. Another way of writing it would be just that, the sum of 1 over n. This is called the harmonic series. I actually don't really know why the word harmonic is used for this and geometric is used for the other one, but these are the names that people have been using for hundreds of years for these two types of series. The geometric series is like actually a whole bunch of examples all tied together, because this R could be anything, and what it adds up to depends on what the R is. The harmonic series is just like one specific thing. It's just this. There's no R which could equal different values or whatever. This is the harmonic series. What does it add up to? This one actually diverges, and this is an important thing to know. The harmonic series diverges. This is a little surprising, I will say. This diverges parenthetically, even though the terms themselves become very small. Right? 1 over n, like as you go down the list here, these terms get smaller and smaller. And so you might feel like if the terms are getting smaller and smaller, then when I add them all together, even though there's infinitely many of them, like the ones towards the end are super small. So you might feel like they should actually add up to a finite answer, but in fact they do not. This diverges even though the terms themselves become very small. I want to try to convince you that this one actually diverges. So here's why it diverges. There is a weird trick for showing why the harmonic series diverges. We'll show that the series of partial sums, the SNs, because this is what, whenever you're talking about a series converging or not, really you're talking about the sequence of partial sums. This, we're going to show actually the SNs goes to infinity for big n's. All right? And the way to do this is a cute trick. I want to look only at the powers of 2. So I'm only going to look at like S1 and S2 and S4 and S8, only the ones where the n is a power of 2. So S1, of course, is just 1. S2 is 1 plus 1/2. S4 is 1 plus 1/2 plus 1/3 plus 1/4, right? Remember, this is how the harmonic series looks. It's always 1 over n, where n, just increases forever. That's S1, S2, and S4. Check it out. Here is a cute trick. I am going to consider those two guys together, 1/3 and 1/4, and I'm going to use an inequality here and change that 1/3 into a 1/4. Right? I put a greater than sign because 1/3 is bigger than 1/4. A third is more than a quarter. All right? And now check it out. What do these numbers add up to? Actually, this is 1/4 plus 1/4, which is 1/2. So this is 1 plus 1/2 plus 1/2, adding up to 1 plus 2/2. Of course, this is just 1 plus 1, although for reasons that you will see in a moment, I'm going to write it as 1 plus 2/2. All right? So just by doing this little trick, you can see S4, the fourth partial sum, is actually bigger than that. It's bigger than this. This is 2, all right? Okay, what about the 8th partial sum? I'm going to do a similar trick. on S8. So this is 1 plus a half plus a third plus a fourth. I'm going to write them all out. You got to go all the way up to 8, all right? But I'm going to do a similar grouping. I'm going to group the 1/3 and the 1/4, like so. And then I'm also going to group these guys, right? Take those 4 things. And I'm going to do a similar inequality like I did before. So this is going to be greater than, I'll leave the first two like they are. But this, 1/3, 1/4, I'm going to change to 1/4, 1/4. 1/4 and 1/4. All right? And that's true. I mean, that's legal because I put a greater than sign here because 1/3 is more than 1/4. And in the second bracket, I'm going to make these all 1/8 because these fractions are all more than an eighth. An eighth is like the smallest of all of these fractions here. So over here, I'm going to make these all 1/8. 1/8, 1/8, 1/8, 1/8. In this little bracket right there. And the thing to notice here is that the 1/8, this is 4/8, which adds up to a half. Everything in each of these brackets adds up to a half. All right, so this is the same as 1 plus a half here, plus a half here. All right, Dem's brackets, I'm bracketing off the things and they add up to a half. All right, and so this is the same as 1 plus 3/2, right? The next one I would write, I'm not going to write it just because it's the same thing but like super long. I would go to S16, and then when I go to S16, I would write one block of a fourth plus a fourth, one block of a bunch of eighths added together, and then another block of 8/16 added together. This is how you would continue this pattern here. All right, and that one would add up to 1 plus 4/2. So generally speaking, in this way, we can show S2 to the power n. Like S8, 8 is 2 to the 3. And when I break it into those blocks, I have 3 blocks that add up to a half. In general, you can say that. The term 2 to the n, you can break it into n different blocks, each of which add up to a half. That's the trick here. S2 to the n is 1 plus n/2. All right? And now I ask you, what does this look like when n goes to infinity? Sorry, I shouldn't say equal. It's greater. All this time I'm talking about greater thans. Sorry about that. Greater. It doesn't matter though. Now we wonder, what happens when n goes to infinity? The answer is this part becomes infinity if the n goes to infinity, and the s's are even bigger than that, which means the s's also go to infinity. All right? The s's here you can see are larger than this part, but this part is becoming infinite when the n goes to infinity. So what happens when n goes to infinity? The answer is 1 plus n/2 goes to infinity, but S2 to the n is bigger. So the s's also go to infinity. All right. And so, in conclusion, so Sn diverges. So that means, and this is the really important thing, the sum 1/n, n equals 1 to infinity, diverges. All right? It's because of this weird trick with the powers of 2 thing. This is a strange trick, and I would not expect you to remember how to do that little argument. And it's not terribly important. Like it's not that we're not going to do that trick in other contexts. So, but anyway, this is why the harmonic series diverges. All right. This I will just say is, and this is a point that we are going to come back to. I don't think later today, but later, soon enough, next time probably. I will just say, note. This is similar to the integral 1 to infinity 1/n 1 over x, sorry, dx, this also diverges. All right. These are not the same as one another. The sum and the integral are not the same. You could think of the sum as representing sort of areas of blocks. 1 1/2 and 1/3 would be like here, and 1/4 would be like here, right? That's the sum, whereas this integral represents the area under the curve of 1 over x, right? So they're not the same, although they're kind of similar. I mean, these blocks are sort of representative of that area in some way. They're not equal areas, but it shouldn't be surprising that they have a similar behavior in terms of their divergence. All right, but this connection actually is something that we are going to talk about at length, probably next time. I don't think we're going to get there this time. All right. Anyway, that is the harmonic series. So I will just say it again. It's strange that the sum 1 over n diverges, even though the terms go to 0. Right? The individual terms, if n goes to infinity, the individual terms go to 0. But that doesn't mean the sum converges. The sum still diverges, all right? So this is a little strange, even though the terms go to 0. What we're going to, our main discussion for the next several weeks is we're going to talk about, we'll discuss various, and if you look at our checklist, you will see we are going to discuss various what we call convergence tests. These are ways of looking at a series and telling if it converges or not. All right? We have already seen for a geometric, it's easy to tell. It depends on what the r is. If the r is less than 1 in absolute value, it converges. If not, it diverges. All right? But in more general cases for non-geometric series, we're going to discuss various convergence tests for series. The idea is to look at a series. I give you a series and you say if it converges. In general, this is a very hard thing to do, and really it's kind of like impossible. There is no general method for doing this in all cases, even like using all of modern mathematics that is currently known today. There are some series where it's not clear what you're supposed to do, how to tell if it converges or not. All right. And our simplest test. So one fairly easy way to see if a series diverges. And this is so simple or like well known that it doesn't really have a name. The various convergence tests have names to them. But one easy way to see if a series diverges is, I'm going to write this as a theorem. Actually, I'm going to write it kind of the other way around about converging, but it says if the sum n equals 1 to infinity an converges, then the lim an is 0. All right. If the series converges, then the terms themselves must go to 0. And this is a quick way that you can sometimes use to show something does not converge. So I'm going to write this equivalently. If you write it sort of the other way around, it says if this thing converges, then this limit is 0. To think of it the other way around, you could say if the limit is not 0, then it does not converge. That's the equivalent version read the other way around. If the lim n goes to infinity, an is not 0, then the series an diverges. All right. These are two logically equivalent statements. I'm just saying it the other way around, all right? This is a nice, when you write it in this way, the second way I wrote it, it becomes a nice way to show that a series diverges by showing that the limit of the terms is not zero. Then it diverges. All right? Can we talk about why this is true? Actually, there's a very cute little demonstration. I want to do the proof. It's very simple, but I'm going to prove the way that I said in black there. So we begin. If you're trying to demonstrate a if-then, you assume the if part. So I'm going to say that the sum of an converges. And my goal is to show that the lim of an will show the lim of the an equals 0, right? That's what the statement in black says. If it converges, then the lim is 0. So we assume, imagine that this thing actually converges, and then I'm going to show that the lim equals 0. Now, what it converges to, let's say I just want to give it a name. Let's say it converges to some value to, I'll call it S, right? This is a real number. When you say the series converges, that means like it actually adds up to something. So whatever that number is, I call it S. All right? Then S is the limit of the partial sums. Because that's what it means for a series to converge. And also, here's the cute trick. Also, Sn, remember, Sn is a1 plus a2 up to an, right? If I were to write Sn minus 1, this is a1, a2 up to an minus 1, which is like the previous one. This is all the way down to n. This is stopping 1 early, all the way down to 1 less than n. And if you subtract these, Sn minus 1, the answer is just an. I meant to write and. An is Sn minus 1, right? That's because it is. Sn means you add them all the way up to an. Sn minus 1 means you add them all up, but you stop 1 early. And if you subtract them, all the other ones cancel, and you just get an left over. All right? But this is almost over. What if I take the lim on both sides here? Do the lim. It says lim an equals, over here, lim of Sn minus lim of Sn minus 1. But what is this on the right side? Lim of Sn, as n goes to infinity, that equals S. I mean, that's what I said over here, right? The Sn's, the partial sums, that goes to, the limit of that is just whatever the series value is. And lim Sn minus 1, that also approaches S. So when I do the limit, this one also is S. That's because I'm imagining the n becoming infinity here. And when this n goes to infinity, you get S. Well, when this n goes to infinity, you also are going to infinity here, so you also get S. All right? The fact that there's like minus 1 doesn't matter. This sort of lags behind by 1 step, but in the limit, as n goes to infinity, you're going to get the same thing. And that's 0, right? S minus S is 0. So what I just say, lim an equals 0. And that's what I said at the very beginning. That's what we were going to show. The lim of an is 0. All right? So anyway, this allows you to show that something diverges. That's typically what we use this theorem for. We use it in the red version here. If the lim of the terms is not 0, then the series diverges. So this is a good way to show something diverges. For example, we've already talked about this example before, We talked about this last time. The sum of minus 1 to the n, that's, minus 1 plus 1 minus 1 plus 1. Talk about this on the playground. Did you see? I got a comment on my YouTube post of this from last time. I don't think it was from one of you. Someone said I'm enjoying talking about this on the playground. I assume is a joke. I appreciate it. Random internet person. If you're listening, thank you. All right. I should address the chat, shouldn't I? More often? Yeah. Check it out, chat. Does this diverge? Remember what we just said here. If the limit of the terms is not 0, then it diverges. And that actually is true here, right? Those terms individually. So here, lim of the terms. What is that limit? This limit doesn't exist because the sequence is, this is a lim of, if I write out the terms, minus 1, 1, minus 1, 1, right? And that limit does not exist. So this diverges. So anyway, lim of minus 1 to the n is definitely not 0. So that means that the series minus 1 to the n diverges. All right? This is a quick and easy way to show something diverges. You just argue that the terms on the inside, their limit is not 0. All right, here's another one. How about 3n cubed minus 7n over n cubed? And your job here, show it diverges. Just like above, it suffices to show that the limit of the terms is not 0. So let's just try and find the limit of the terms. The lim of the terms is 3n cubed minus 7n over n cubed, right? And see what we get. If we don't get 0, then that means the series diverges. Anybody remember how to handle a limit like this? There's actually ones on the homework like this, and perhaps you just remember anyway. Yeah? Do the ratio. Yeah, you should, ordinarily I would say divide out by the highest power of n, although perhaps you remember there's like a special, you can like memorize answers in the case when the powers are equal on the top and the bottom. It's true that you always get the ratio of the coefficients on the top and the bottom. But if I were going to write out the details, I would divide everything by n cubed, right? So I'd say this is 3n cubed over n cubed minus 7n over n cubed divided by n cubed over n cubed. That's 3. This is minus 7 over n squared divided by 1, right? And then I take the lim. It makes that 7 over n squared go to 0. And then all that's left over is 3 and 1. So this is 3 minus 0 over 1. The answer is 3. All right. She said, just look at the ratio. So it is a fact, and if you want to do it this way on your homework or on a test or whatever, that's fine. It is a fact that if the powers on top and the bottom are equal, then the answer that you're going to get is always the ratio of the coefficients on the highest degree power, or the highest degree term on the top and the bottom. In this case, 3 over 1, which is just 3. Okay, anyway, what I was saying, this lim is 3. So the lim of the terms is not 0, because it's 3. That means the series diverges. Right? This is a nice way to show something diverges. Any thoughts about that one? I got one more. This one is extra cute. How about the sum of sine of n? One of my favorite weird examples. The sine of n. Again, I want to demonstrate that this diverges. It is enough to show that the terms do not go to 0, so I should be thinking about what is the lim of sine of n? Anybody recall? We talked about this example before, I think. Does this have a limit? or does it diverge? What are your thoughts? Yeah?
It'll just bounce back and forth between values.
It bounces back and forth, yeah. So what does that mean? Does it converge or diverge? It diverges, yeah. This does not actually approach a specific number in the answer. It basically, since you're plugging in whole numbers, this is like sine of 1, then sine of 2. You're going to get essentially random values between -1 and 1, but it never converges to anything. This diverges. So in any way, it's not 0. So that means this series also diverges. All right. That's how we do it. All right. Maybe I'll give we can start a little bit of chatting about what we're going to talk in detail about next time is the first of our convergence tests. So convergence is hard. Convergence be hard, as they would say. Convergence is hard to tell what things add up to. For a geometric, it's easy. We already know the formula. If the r is less than 1, it adds up to a over 1 minus r. But even in sort of slightly different examples, this can be very hard. Like, for example, we have just been talking about the sum 1 over n. This diverges. What about the sum 1 over n squared?
It converges.
It converges, yeah. Do you know what it adds up to? Are you familiar with this?
It's a p-series, right?
It's a p-series. Yeah, that's right. There's a name for this. This 1 over n squared, this is called a p-series, if you've heard of that before. This actually converges. Do you happen to know what this one converges to?
I don't remember.
I'd be impressed if you remember. This is actually a very weird example. So this one, if I were to write out the terms, it looks like 1 over 1 and then 1 over 2 squared, 1 over 3 squared, 1 over 4 squared, right? It's adding up where the denominators are each squares. The next would be 1 over 5 squared, which is 1 over 25, etc. Actually, people have been considering this for a long time. You can try these values out on your calculator, just add up 5 of them, add up 6 of them, and see if it seems to be going to infinity or seems to be converging. Actually, this one does converge, and it turns out this was first worked out in by one of the OGs, all-time greats of mathematics. This guy, I hope you are saying his name properly in your head right now. Euler. This is a German guy. Don't say Euler. You'll sound stupid if you say Euler. It's Euler. Anyway, in 1730s, figured this out. The sum 1 over n squared. This adds up to, I'm sure you were about to say this, pi squared over 16. Huh? Am I right? This is a true fact. This, in my opinion, is totally insane that this is true, but it really is. If you add up the reciprocals of the squares, they add up to pi squared over 16. In a sane universe, there's no reason why anything like that should be true, but it turns out that it is true. This is one of those things that mathematicians regard as beautiful. Just the fact that you can add up I don't know, to me this looks fairly ordinary, but this adds up to something involving pi squared. Very strange indeed. Euler figured that out. But actually there are big unsolved questions, I will just say, regarding, still unsolved today, regarding the sum of 1 over n to the power x for various x. So what I just did was 1 over n squared, if the x was 2. But you could also consider 1 over n cubed, or 1 over n to the 4, or even other values of x here, like non-whole numbers. You could still do that and try to add it up. 1 over n to the 1/2, for example. Or you could even do complex numbers for the x. That's very weird, but actually people study this a lot. And there's what I believe most people, if you can ask, poll the other math faculty about this. If you ask people, what's the most important unsolved problem in mathematics today? I think generally people will say it is the Riemann hypothesis. And the Riemann hypothesis is a specific question which has existed since the time of Riemann. Riemann was like in the late 1800s, and he posed a very specific question about, can you calculate this series for various x's? The short answer is nobody actually knows how to calculate all of these numbers for various x's. There are certain specific values that we understand. For instance, if x equals 2, it adds up to pi squared over 16. But actually, it is not generally understood what kinds of answers can you get if you use other x's here. I believe it is known for all whole number values of x, but for the other ones, and especially the Riemann hypothesis specifically is about the complex number values of x. This is one of the biggest unsolved problems in math today. Look it up if you're interested. If you got any ideas, let me know. I'd be happy to look at your ideas. The Riemann hypothesis is one of a list of 7 problems. Perhaps, I don't know if you've heard about, in the year 2000, the mathematical community came up with a list of 7 unsolved problems, which are now called the Millennium Prize problems. And there is a $1 million prize for the solution of each of these 7 problems. And since then, the 7 problems were posed in the year 2000. Since then, one of them has been solved, but you got 6 more, so get to work. And the Riemann hypothesis is kind of the oldest and most distinguished of all 7 of these problems. I am not, I am a mathematical researcher. I am not currently working on the Riemann hypothesis. This is kind of like, if I told my friends I was working on the Riemann hypothesis, they would sort of laugh me out of town. Just because, like, I'm, whoever eventually figures this out will be like the greatest mathematician ever, and I am not. I assume I'm not on that level. It's kind of like. I remember when my kid was in kindergarten, one of their friends told them, yeah, I like to build things in my basement, and I'm working on making a shrink ray in my basement. This is like, if I said, I think I've proved the Riemann hypothesis, you should think like, come on, man, get real. Anyway, this is a big deal, is all I'm saying. This question of, can you just look at a series and tell me what it converges to? Even in a fairly straightforward example like this, all of modern mathematics is still working on the answer to that question. Anyway, let's talk. We got 10 minutes left. Can we talk about the first of our convergence tests? It's called the integral test. So given that there are certain series which are just way too hard to tell what it adds up to, we're going to kind of take a step back and say, all right, rather than saying what it adds up to, can we at least say if it converges or not? This is still a very hard question, but we're going to talk about several different tests which you can sometimes use to say if it converges or not. None of these tests work in all cases because, like I said, it's actually not, even today, not understood mathematically, all cases for series. But they work. Sometimes you can use each test on different examples. You might have to use this or that test. So anyway, the integral test is, this is what I was alluding to before. We can compare a series to a certain integral. And there are relationships between a series of a certain formula versus the integral of that same formula. And what I was getting at before was, for example, the sum of 1 over n equals 1 to infinity, versus the integral from 1 to infinity of 1 over x dx. All right? Now, these are not the same. They're not equal. Well, they both diverge, so maybe in this example they're equal. But these two things, they can both be represented as areas. And I would represent, I'm going to try to draw similar pictures to what I drew a few minutes ago. But I'll try and draw it a little nicer this time. So the integral would be the area. This is my function, 1 over x. The integral, so the integral would be this area under the curve, all of that, right? That red shaded region is the integral 1 over x dx, 1 to infinity. And how would I represent the series 1 over n? I would write the series 1 over n. You can fit it into this picture by making it into a Riemann sum. So this plus this plus this plus this, right? That first one has area 1. The next block has area half, a third, a fourth, right? I know this might be hard to draw this picture. I hope you can see it fairly well, though. So the red area is the integral, and the series is the area of the boxes, right? And so, I will say again, they're not the same. Like the boxes you can see are stretching past the curved area, but they seem kind of similar at least, all right? They're not the same. These aren't necessarily equal. But they are related. So generally speaking, there is a relationship between the sum 1 over n, not 1 over n, but just, let me write the integral first. The integral of f of x dx from 1 to infinity, this is related to the series f of n equals 1 to infinity. So if your series can be written using a formula that looks the same as a continuous function, then the area under the curve on the left side is related to the value of the series. They are not equal, because as you saw, like those boxes are not the same as the curved area, but there is a relationship between them. And maybe this is something I want to get into more detail later, but I will just say either, this is the punchline, either they both converge or both diverge. This is the fact about the integral test. And I think maybe I'll leave it at that. So we will talk about the details of how to think about this more next time. All right.